This is a typical example of a coupled differential equation question in population dynamics. At the start of the year 2000, a survey began of the number of foxes and rabbits on an island. At time t years after the survey began, the number of foxes, f, the number of rabbits, r, on the island are modeled by the differential equations given below. The first question is to show that these can be reduced. These two ordinary differential equations can be reduced to the second order differential equation given in A. I'm going to employ Newton's notation, which is that df by dt can be written as f dot, and similarly with r. So I've done the solution already, well, at least most of it. So I'm just going to briefly go through how to do it. So for part A, what I've done is I've differentiated df dt to give f double dot as 0.2 f dot plus 0.1 r dot. I've then used the first expression that we had to rewrite it. So f dot dot, obviously we have 0.2 f dot, that was just given to us. But then in place of r dot, I've used the dr dt equals minus 0.2 f plus 0.4 r. I've substituted that in for dr dt. Then I have used the fact that 10f dot is 2f plus r. So that I've got from the first equation by multiplying it by 10 on both sides. I've rearranged that to get that r is 10f dot take away 2f. Then I've substituted that in to my f dot dot. So I have f dot dot is 0.2f plus 0.1, and I'll just redo this bit. So minus 0.2f plus, and then it's 0.4 times 10f dot take away 2f. So if I do that, 0.4, I get 4 f dot take away 0.8f minus 0.2f take away 0.8f is just minus f. And then I get f dot dot is 0.2 f dot take away 0.1 f, that's expanding this bracket, and then plus 0.4 f dot here. Then I take everything over to the left hand side. I will get that f dot dot take away 0.6 f dot plus 0.1 f equals 0, which is the required form in part A. Then for part B, remembering that the equation was f dot dot, this was the second order ODE differential equation, f dot dot take away 0.6 f dot plus 0.1 f equals 0. I've written down the complementary or auxiliary equation, k squared take away 0.6k plus 0.1. K squared corresponds to the second differential, the k corresponds to the first differential, and then the constant corresponds to the form of f, or the coefficient of f. My solutions to this is a quadratic. My solutions are 0.3 plus or minus 0.1i, just using the quadratic formula. And then that gives me the general form of the solution as f of t. So this is the complementary function, I should say. Of course, because this is a homogeneous second order ODE, the right hand side is 0. That means that my general solution for f is either 0.3t and then a, so some constant, cos 0.1t plus b sine 0.1t, which is what they wanted for part B. Then for part C, they want us to find a general solution for the number of rabbits on the island. Now this is quite a tedious process, but it really helps if we write the forms in a certain way. So I've got f dot is, and I've worked out f dot by just differentiating my previous expression for f. And I just used the product rule for this. So either 0.3t, differentiate that, you get 0.3 e to the 0.3t. That's then multiplied by the bracketed expression plus e to the 0.3t, just unchanged, multiplied by the derivative of this bracketed expression, which is minus 0.1a sine 0.1t plus 0.1b cos 0.1t. And then I've used a shorthand for r. I've just let c be the cos term and s be the sine term. And then it's a lot easier to see what is going on. So I can see that r, and again, I'm getting this r from the, I'll show you where I was getting this from, sorry about this. I'm getting it from here. So to get r, I just do 10f dot, take away 2f. I've just done that here. So I've multiplied my f dot, so this, by 10, and that gives me 3 e to the 0.3t a cos plus b sine plus, and then the 10 here, I've multiplied into the bracketed expression, so I just get 1b cos take away 1a sine, and then of course we've got take away 2f, so take away 2 e to the 0.3t plus a cos plus b sine times a cos plus b sine. Now this makes it easier to write my expression for r. It's a lot more instructive. So if I look at my cosine terms, you can see you've got 3 e to the 0.3t a cosine plus e to the 0.3t times b cosine, take away 2 e to the 0.3t times a cosine. So effectively, we're going to have 3, if we ignore the e to the 0.3t, you have 3ac plus bc take away 2ac, and that just gives you ac plus bc. So this is how I've got a plus b times c in the bracket expression. And then similarly for the sine, I just change color here. So similarly for the sine, don't let me do that. We have 3b sine plus, then it's, well, sorry, minus a sine, take away 2b sine. So then we get b minus as in the bracketed expression. And this will make the rest of the question somewhat easier. So they want the general solution. We've got the general solution now for the number of rabbits in the island at time t years. And then for D part 1, at the start of the year 2000, there were 6 foxes and 20 rabbits on the island. According to this model, in which year the rabbits predicted to die out. So what I've done for D part 1, you need to work out A and B. So we're told that at the start of the model there were 6 foxes on the island, which means that f of 0 is 6, and obviously cos of 0 is 1, sine of 0 is 0. That leaves you with A. So A is 6. Similarly, R, the number of rabbits at the start was 20. So R of 0 is 20, which is A plus B, because again, cos of 0 is 1, sine of 0 is 0, and that leaves you with B as 14, given that A is 6. So now we have the constants, and what we want to do is work out when the rabbits are going to die out. So if I assume they die out at some time t tilde, I know that r of t tilde is going to be 0, because that's when the rabbits are at 0. So I've substituted in 0 into the right-hand side of my expression for r, and I'm obviously using the specific time t tilde, and that's not particularly important. I get e to 0.3t times 20 cos 0.1t, because that's obviously the, if I just show you the expression again, a plus b is 20, then b take away a, 14 take away 6 is 8, and that's how I've got this 8 sine 0.1t. E to the 0.3t is never going to be 0 for any value of t, therefore 20 cos 0.1t hat, or t tilde, plus 8 sine 0.1t tilde must be 0, which we can rearrange. You can subtract 20 cos 0.1t from both sides, then divide both sides by sine, sorry, other way around. Subtract 20 cos 0.1t from both sides, divide both sides by sine 0.1t, you will get tan 0.1t, or t tilde, equals minus 2.5. We can solve this trigonometric equation rather easily. We take inverse tan or arctan of both sides, you get 0.1 t tilde is roughly minus 1.19 plus pi, because obviously we're looking for a time in the future. So we need the solution which is to the right of pi over 2. That gives you approximately 1.95. Now, the actual value I'll get on the screen. So I'll just put this here. So the actual value, we can do shift tan minus 2.5 and then add pi. And we actually get 1.951. That's 0.1 t. So if we multiply it by 10, we'll obviously get 19.51, 19.513. So that is how many years after the start the rabbits will be extinct on the island. So we have to say, well, if it starts in the year 2000, this is going to be about roughly halfway through 2019, just adding on the time. And then part two, this is a bit of a, what makes this tricky is that you have to, I think, use the exact value here. So we want the number of foxes on the island when the rabbits die out. So we need to use the time that we worked out, 19.5 approximately. I just got to remind myself what f was. So f was this expression. So if I just put that here, if it will let me, there we go. That's my f, remembering that a was, what was a again? A was 6 and b was 14. And they were added. Yeah. And if I substitute that value in, it should give me the correct answer. So I recommend doing it in stages, but they should give us it. So e to 0.3 times what I just had. And obviously make sure you're in radians. 6 cos 0.1. And I don't typically suggest substituting something like this straight into a calculator. And that gives us 3,754 approximately. Now, the mark scheme for this says 3,750, but this is the more exact solution. Again, with this sort of model, it's not a guarantee. This is a model, so approximately 3,750. Then use your answer to part 1 and 2 to comment on the model. I suppose, well, the model's not perfect because you've now reached a point where there are no rabbits on the island, but there's still a significant number of foxes. That's not a sensible solution. If you completely run out of rabbits, you'd think the foxes would decline very quickly.